In this video, I want to have a look at calculating the area of segments. So a segment is part of a circle that's been cut off by a chord. So in this example here, this is the chord going, the straight line going from this point along here to this point here. And this is what's called our minor segment. There's also a major segment in there, so that's everything in this circle that's not coloured in yellow. But in this one, we're going to have a look at how we can calculate the area of this yellow region here. So to calculate the area of this segment, we're actually going to find the area, that's not a straight line, of this whole sector here. So this whole area in here, very not straight lines. And then we're going to subtract the area of this triangle here. So we're going to do two area calculations and subtract them, but we're going to simplify our formula so that we've just got one formula we can do rather than doing two calculations separately. So we know that the area of a sector is a half r squared theta when theta is measured in radians. And for the area of a triangle, we have the sine rule for the area of a triangle. The sine rule for the area of a triangle says the area is a half AB sine C. So in our case, our C is our theta, and our A and our B are the two sides around that angle. So in this case, A and B are both r, the radius. So that's going to give us a half r squared, because A and B are both r, sine theta. So this is the area of that red triangle. So that's what we're going to have up here. So we're going to subtract a half r squared sine theta. And now looking at this, you can see that we have a common factor of a half r squared. So we're going to pull that out. So we'll have a half r squared outside of theta minus sine theta. So I've just written it a little bit neater here. Now this formula is not on your formula sheet. So if you remember this as it is, that's fine and you can use it, but it may be easier to remember how it's derived. So you have this formula here, the sine rule for the area of a triangle, that's on your formula sheet. And the formula for the area of a sector is on your formula sheet as well. So you don't have to remember this off the top of your head if you remember how we got to this in the first place. So our example asks us to find the area of the minor sector formed if an angle of pi on 4 is subtended at the center of a circle with a radius of 5 centimeters. So we're going to put that information into our formula. So we're going to have area equals a half times r squared, so that's 5 squared, outside of pi on 4 minus sine of pi on 4. Right, so we can simplify this bit out the front. 5 squared is 25, so this will give us 25 on 2, outside of pi on 4. Now this bit here, pi on 4, that's equivalent to 45 degrees. So pi on 4 radians is 45 degrees. And that means that this is one of our special triangle values, or our exact values. So the triangle on your formula sheet says 1, 1, root 2, and it has 45 degrees in each of the corners. So we can use that because it's going to apply to pi on 4 as well because they're equivalent. So that means that sine of pi on 4 will be 1 on root 2. So now I'm going to expand this out. So we're going to have 25 pi over 8 minus 25 over 2 root 2. I'm going to rationalize the denominator of this second fraction. So we're going to have to multiply the numerator and the denominator both by the square root of 2. So we'll have 25 pi on 8 minus 25 root 2 over 4. And if we put that all in one fraction now, to get them to have a common denominator of 8, we'd have to multiply the numerator and denominator in this one both by 2. So we'd have 25 pi minus 50 square root of 2 all over 8, and that's centimeters squared for the area of that segment. Now some questions will ask you just to round that off, say to 2 decimal places, and you can just put it in your calculator from way up here, as long as you have your calculator in radians. All right, so that's having a look at the area of segments.